Welcome to Software Overview Part 2. If you have not seen Part 1, please check that out here. In Part 1, we describe the different types of software that we can build on computing devices, from traditional to server to cloud to mobile and embedded. So please check that out to get a better feel for the types of software in the environment. In this video, we're going to concentrate on how do we build software optimally to run on machines today. What are the concerns we should look out for? What is the difference between a RISC and assist computer? And why do I need to know that for how I write software? Why is it better sometimes to sort an array before I call for it? How does that affect where things land in cache? All of these questions that you've probably never asked yourself, but by asking could vastly improve the performance of your software. I'd like to start by looking at a little bit of history and ironically how cyclic it is in nature. If we go back in time and we look at programming problems in the 1960s, 70s, 80s, they'd be dominated by the lack of memory that a software engineer had to work with. That was by far the biggest constraining factor. RAM was extremely expensive and hard to come by, and if we go back far enough, it wasn't even random access memory. Sometimes it was sequential, which made it even more difficult. So as computer hardware has grown, software engineers have had more and more layers of abstraction, more and more physical resources to work with, and they ended up writing their code further away from the actual hardware. This led to a situation where you didn't necessarily need to know the hardware as well. Well, as history has shown us so many times, what was once, new and then became old is now new again. And in the modern world, we're working our way right back to where we were. What's becoming more and more prevalent nowadays is Internet of Things, these small embedded devices with limited memory and CPU, running one application that has very little, if any, abstraction from the hardware. So once again, as developers, we find ourselves needing to know and understand our systems more intimately. And to be honest, knowing your system, even when you are dealing with a more traditional software stack, is extremely helpful in getting performance out of your software that you probably didn't even know that you could tap. If we go back far enough and we look at how early hardware was developed, ironically, the lack of memory was such a prevalent problem that decisions were even made on hardware architectures themselves and how they were built. The physical hardware was built in order to minimize the amount of memory that would be needed. Early computers, and we're going to talk more in an upcoming video about RISC and CISC and what the differences are. But CISC, which is complex instruction set computing, was chosen over RISC, or a more RISC approach. I mean, RISC came later, but we went towards a complex instruction set, meaning more instructions that you can have less instructions in your program that accomplish more in hardware because it was actually cheaper to build a more complex CPU with more intricate hardware than it was to have more memory to run your programs in. And once again, as we look at IoT, we're seeing this same pattern evolve, where the needs of hardware are being driven again by the needs to create software in a very small, low-powered, low-impact environment. So what are some of the other things that we as programmers should look out for in the world that we can write our software more efficiently to deal with better? Well, in the modern world, the big problems that we have, even in the traditional sense, is the parallel nature of processing today. Gone are the days when we would simply double the speed of a processor every 18 to 24 months by doubling its clock cycle. In fact, the clock speed of computers has not, appreciably jumped forward in the last decade. We've had, maybe a 10 or 20% increase, on average in this area. So what have we done instead? We've gone to multiple core, multiple processor systems. This means that our software has to be aware of things like race conditions and problems that might arise from overwriting data from multiple CPUs, and when we read from data and when we can read from data. This is a very complex problem to solve because in fixing the problem, you could actually take away all of your performance gains if you restrict yourself to only running on one processor. You may have heard of the terms immutability or mutability used a lot more often in software engineering today. Immutability is this idea that once we create an object, we're not going to change it or some data that we have in memory. This is important in parallel computing because if we have immutable objects, we don't need to be concerned when we're running on multiple CPUs that if we change that object, it could affect some other aspect of the program. This does mean that we use more memory, and it means that we give up in some other places, but what it achieves is a better parallel nature of programming. So understanding these basics, again, can lead us to a position where we can write much more efficient code. Another thing that is good to understand is that hierarchical model of memory that we discussed. So if you go back to the video here, you'll see that we looked at memory as a hierarchy. We said as you went up the triangle, you had faster, smaller, more costly types of memory, and as you go down the triangle, you have larger, cheaper, and slower types of memory. And because we have this hierarchical memory, if we do it correctly, we should be able to get to the place where the CPU can run as efficiently as possible because the CPU is actually faster than the memory. But if we put the speediest memory next to it and we do some creative things like loading a batch of things out of memory into the CPU at once, then maybe we can keep the CPU busy. And if we spend enough on the memory at the top of the triangle to make it just big enough and just fast enough to support that CPU, then we can have all the storage space at the bottom of the triangle that we want. And understanding how this works is important for us. If we, say, have a large array of data and we know that we're going to be accessing it in a particular order, making sure that information is sorted correctly before it goes into cache will result in many fewer cache misses, meaning that all of that information will be available when it's needed without having to make the timely trek to DRAM to actually retrieve the information and fill it into cache. Other things are important too, especially in the mobile world. Energy efficiency is absolutely paramount. If your application burns through a user's battery because you feel that you want to have the absolute best, say, localization on a GPS application, and it's got to be pinpoint accurate at every moment, the trade-off you're going to be making there is that you're going to be burning through a user's battery. And they're not going to be happy about that, and they're probably going to delete your app. So there are always trade-offs, especially with energy efficiency in today's landscape. Another big one is the distributed nature of modern applications. 99 out of 100 applications built today are depending on some way and some other services that are available on the internet. It just doesn't make sense to recreate the wheel at all times. So if I'm using a Google Maps API service, I have to take into account that I have to make a high latency network call over the internet to get that information and wait for it to be returned. So I don't want to have the user's experience diminished because they're just hanging there waiting for this network call to happen that sometimes may happen quickly and other times not so much. So I should be building my applications in such a way as to minimize that so that things are asynchronously updated and users have a good experience using them. So the success of a programmer and the success of your program depend on your understanding of the actual environment in which you're building your software and knowing, am I building it for a traditional hardware architecture because these are my concerns? Am I building it for an embedded one because these are my concerns? It's more than just knowing that in the year, say 2020, these are the major concerns. It's about knowing which concerns for which type of hardware. In computer science, we have these 8 great ideas that have been around effectively since the beginning of programming and computers and affect our lives in many, many, many ways. And if we as software engineers know and understand and respect these ideas, we'll see that not only can they be used to make hardware faster, but they can be used to make software faster, and they're always most likely going to be able to be used in the future. So these are not, constrained to software today or hardware today. They are going to be ideas that we can apply to many different aspects of what we do and in the future as well. So the first one here is Moore's Law. Now, Moore's Law was something attributed to Gordon Moore, who was the founder of Intel. And he essentially said that every 18 to 24 months, the amount of transistors on a silicon chip will be able to double in effectively the same amount of size. So if I have a silicon chip that, say, make up a numbers 10 centimeters by 10 centimeters square, I can double the amount of transistors that I can etch into that silicon through refining the manufacturing process every 18 to 24 months at the same cost. So meaning that that chip would cost the same 18 months later, even though it had double the transistors in it. Now, what does this mean for us? A lot of people think this means that the processor is going to double in speed. And that's not necessarily true. So when I was very young, computers would actually double roughly every 18 to 24 months in clock speed. I could be pretty well assured that if I bought, and I did, my 386 20 megahertz machine at a certain point in time, that within 18 to 24 months there would be a 386 40 megahertz machine. And this trend would continue, and it did. Today, we've pretty much reached what we can do heat dispersion-wise with clock speeds, but what we're finding is that if we keep doubling the transistors, then we can put those transistors to work that affects the speed of the processor just as much. So we can add more cache, we can add more pipelines, we can add better multiple execution units, we can add better improved specific hardware to deal with multimedia function and all kinds of things that speed up the overall experience for the software. So Moore's Law just says we double those amount of transistors. Now, what's interesting is this is struggling currently to maintain. It has been pushing forward, and we are still close to doubling every 18 to 24 months, but there is some debate on just how much further we can go. We've reached the point now where, we're looking at, a small amount of atoms across the middle of the transistor, say somewhere between 7 and 10, where if we go too much smaller, there's just simply not enough atoms there to prevent the electric charge from, when you have the control wire off, from bleeding across the top of the transistor and getting to the other side anyway. So that makes for a situation where you can't always trust the transistor. You need a certain amount of insulation when the transistor is off because the control wire is off, and then when you apply the charge to the control wire, then you have the transistor conducting electricity. So this is something that is a problem, and there have been creative solutions in the past, and there is no reason to believe that these creative solutions may not also present in the future. That said, it is a challenge, and it'll be interesting to watch. Another big one is abstraction. Now, I did an entire video on abstraction here, so please check that out. A third is common case fast. Now, common case fast is simply the idea in computer science that if we want to attack a performance problem or any problem, that it makes the most sense to evaluate what is the biggest kind of gain that we can achieve. What is the low-lying fruit, so to speak, that if we attack this, we'll get the best gains. When we looked at Amdahl's law, we looked at the idea that if we wanted to have a 5x gain on our software, let's say we wanted our software to run 5 times as fast, that's our goal, and our software 80% of the time that it was doing computation was doing multiplication. Common case fast tells us that, well, since 80% of what that software is doing is multiplication, if we attack multiplication as the thing that we want to refine and make faster, we will have the biggest gains towards our goal, because spending the amount of time on the other 20% to eke out some gain is just not going to be the most efficient way to use our time. Let's attack the 80 and make it as fast as we possibly can. Now, what we learned with Amdahl's law is that a 5-time gain from just that 80% is impossible, because it's impossible to get a 5x gain out of 80%, because you would need more than 80% to affect that change. In fact, it's going to be extremely hard to get a 4 times gain, because you're looking at a proportional of that 80% and not the whole 100. But regardless of Amdahl's law acting as a corollary to common case fast is something that we can apply to everything that we do in computer science, hardware and software. If we're building a computer chip and we want to make it faster, we can look at what are the biggest bottlenecks, what are the things that cause the biggest slowdowns, and then attack that first. And we can mathematically figure out exactly how much we need to improve on some common cases to get to our goal. We can do this with our software too. If we have some algorithm that is chewing up 80% of the CPU time, refining that, just as we looked at with the multiplication example, will give us huge gains towards the overall performance of our application, since it chews up 80% currently of that whole CPU time. Performance via parallelism is basically the idea that since we're not getting raw clock speed gains anymore like we used to, one of the biggest ways we can speed up our programs is to run them parallel. We can have multiple CPUs, multiple cores, and we can actually just run multiple programs through multiple processors at the same time. We can do more than one thing at once. As we discussed earlier, this can lead to some discrepancies, and we have to make sure that we don't try to update data and cause update anomalies concurrently. So it does require some overhead, but there are ways to manage that, and performance by parallelism is currently one of the biggest things we can do to improve our performance of our software. Another thing we can do, particularly on the hardware side, is performance via pipelining. So a pipeline is simply the idea that a CPU has to go through multiple steps as it executes an instruction, and the pipeline represents each one of those steps. There may be multiple steps to do with the fetch, which is to say get some information from memory. There may be a step or two involved with decoding that instruction to understand what type of instruction it is and what needs to happen. There may be steps involved with the execution of an instruction that require sending it to different parts of the data path to manipulate it in different ways. So if we build more complex pipelines, we can stick more instructions into the pipeline and get more things done at once. We're going to touch on this a lot more later, but think about it this way. If you have to do your laundry and you go to the local laundromat, and the local laundromat's empty, right? Let's just say you're the only one in there, and there's 20 machines and 20 dryers. Let's say that you have the equivalent of what would be 10 loads of laundry. You haven't done your laundry in a long time. Are you going to sit there and do your laundry in one machine, one load at a time? Or are you going to take your load of laundry and stick it in 10 machines, right? You're going to stick it in 10 machines, and then you're going to take out that and put it in 10 dryers, and you're going to be done. And that's the idea behind pipelining. Modern CPUs are not just basically a structure that has one adder and everything funnels through this one part. They have multiple adders, and they have multiple places that they can execute code through your data path that are specialized to performing certain tasks. And by taking instructions or loads of laundry and putting them into different machines, you can get things done more efficiently. Another great idea is performance via prediction. So sometimes it's faster to make blind assumptions to just kind of take a guess. So let's look at an example here. So if you're running a piece of software that has a loop, this is very, very common. Let's say that you have a for loop and it's going to run 1,000 times. Your software might not know when exactly this loop is going to end. In fact, let's say it's not a for loop, it's a while loop. And it's going to run and run and run until eventually some condition changes, some Boolean changes from false to true, right? So our hardware, if it's smart enough, could make a prediction that says, well, I think I'm going to continually make this loop. And I'm going to keep all of my hardware filled to capacity and running as if the loop is going to happen, not knowing whether or not it is. And if I'm wrong, it's going to mean that I have to undo a lot of things and reset. But I think that overall it's going to be faster for me to do it this way, because odds are good that I'm going to continue on this pattern for maybe thousands and thousands and thousands of cycles until eventually something changes, and then I deal with it at that time. And that's this idea of performance via prediction. We're going to look at this in depth with things like history tables and stuff like that, where hardware actually looks at the recent history of some conditionals and looping constructs to try to figure out what it thinks is the most likely outcome. Because when branching happens, which is what happens when something changes, the flow of the program changes, we don't go from, say the instruction at line 10 to the instruction at line 11, but we jump somewhere else. Once that happens, this pipeline and all these other constructs that we've created to speed things up have to get flushed, because now everything that's in them is essentially set up for the wrong thing. So if we can predict those changes before they happen, we save ourselves a lot of time. Now, this is obviously true in our software too. Anytime that in our software we can predict what a user is going to do, we make a better experience for that user. If we know that odds are good that after they load a certain page in our application, that they're going to want to, highlight a particular button, maybe we have it, highlight that area on the screen, right? And do a little like light it up or pulse or something. This is the same idea. I mean, we're not talking about a processor here benefiting from the prediction, but we're talking about the user benefiting from the prediction. We streamline the user's process. So that's what I mean, by the way, about these 8 great ideas being applicable to all areas of computer science. They're applicable to hardware, and we're going to discuss that in depth, but they're also applicable to everything that we do in software as well. Lastly, here is the hierarchy of memory. Now, we've discussed this a couple of times. So this is that triangle that we discussed where the CPU's registers and cache are at the top, and then our RAM, and below that we have our secondary storage, so our SSD or hard drive, and then maybe even storage beyond that. Maybe we have a cloud backup, or maybe we have a tape drive, right? And the reason why this is so important is because as a cost proposal, you might say, well, why don't I just have SSD? Why don't I just have the fastest memory and not even have the slower stuff? Well, the answer is once you reach a certain performance and you have the CPU all filled up with instructions and the data that it needs, and your CPU miss rate is very, very small, or your memory miss rate is very, very small, then it actually doesn't matter anymore how much more of that you have. You can have as much as you want of the slower memory, and that's okay, because you've achieved your goal of keeping the CPU happy and filled with instructions and data. Once you've achieved that, then the only reason you wouldn't want to have, as much cheaper memory as you could afford is essentially that, power, space, things like that. So if you look at embedded devices, they're not always going to have secondary storage. Maybe they have some flash storage just to store, some little bits of data and the program memory. But once you're running, you're just using your primary memory, because there's no need to store anything else long term. And why would you spend the money on it at that point, because it's not used? And why would you use your limited battery life to support it if it's not used, right? But when you look at a traditional system, like a desktop, there's no reason not to have the slower, larger storage, because once you're successful in feeding the CPU everything it needs from the top of the triangle, then you can make the bottom of the triangle as big as you want. The last one here is dependability via redundancy. Now, this is important, especially as we were discussing in the embedded systems world, like when we're talking about autonomous vehicles, or if you imagined a modern plane with autopilot. All of these things have redundant systems because we need some way to make them dependable, and these little embedded devices aren't necessarily the most dependable things by themselves in the world, but they're performing a function that it's absolutely critical that they perform dependably. Now, we also talked about traditional data centers and cloud data centers using commodity hardware. This is, just traditional desktop hardware essentially that is racked in server racks that has better cooling and power supplies, but essentially it's no different from what's in your laptop or desktop today. This hardware can and does fail all of the time. So how do we deal with that failure? We don't want to lose data and we don't want to lose uptime, so we make them dependable via redundancy. We use software to virtualize so that systems can be moved from one physical hardware location to another, or run in multiple so that if one fails, you automatically cut over to your secondary. And the user experience, from the user's perspective, you never even know that it happened. A modern computer, no matter which variation, whether it's traditional or mobile or embedded or even a enterprise class server, they all have the same basic limitation. They are all basic computing devices that have this marriage of some hardware and instruction sets that know how to drive that hardware. It's called the instruction set architecture. We as programmers have gotten away from programming directly in these instructions. They're very hard to read and understand. We like to program in what's known as a high-level programming language. There's lots of good reasons to use high-level programming languages, and we're going to look at that more in a few moments. But how do we get from our high-level programming language to these raw machine instructions that actually drive the computer? And we've talked a lot about abstraction, and of course abstraction is the answer. But now we want to look at some of the specific abstractions that get us there. So abstraction, especially in computer science, can really be viewed like an onion. And you can think of the core of the onion as the actual hardware. That is the thing that we are manipulating with our software code. The first ring of the onion there could be what's referred to as microcode, and we'll talk more about that in some future topics coming up. But microcode is actually a hardware level abstraction that allows us to apply less complex machine instructions, so more machine instructions that then get translated into a more complex single instruction. We'll talk about why in a later date. But above that, then we can think of the regular instruction set architecture kind of contract of that architecture. So, am I giving it an add instruction, a subtract, a load, a store? What action am I asking the computer to perform? Above that, we may have the operating system. Now, the operating system will manage all of the other softwares that are running on the onion in this case, but the computer, and manage the resources of the computer for it, right? And it will say, okay, software A, you can run right now. And then, software A, you've ran for long enough. I'm going to let software B run for a little while. Then outside of that, you have different layers of applications and things like that. You may be programming in a language like JavaScript, for example. Now, JavaScript is an interpreted language, which means it's not actually compiled. When you write JavaScript, you give the text file that contains the JavaScript. I know it ends in a different ending, but it's essentially a text file. And you're going to give it to the JavaScript interpreter, which is 9 times out of 10 or more actually your browser. So it could be Chrome, Firefox, or Edge. And they are going to read this code line by line, and they are going to convert it into machine instructions or send it down the road to get compiled and turned into machine instructions that then actually run on the hardware after going through the operating system and all the way down to the center. So you are many, 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 many layers away from what is actually happening. Now, a more traditional programming language, say like C, you're going to be a lot closer to the center of this onion, but still on the outside of it. A programming language like C takes your program and it compiles it. It creates those machine instructions, the ones that run down here, for you from your high-level code. Now, it also takes libraries from your operating system that deal with I/O devices that you don't want to have to write code for. So, for example, you don't want to have to know how the monitor displays your hello world. You just want to tell the operating system, I need the monitor, which is a resource that you protect, to display the word hello world. Well, your C compiler, in addition to compiling your own code, then gets the operating system library code for dealing with displaying some text on the monitor and combines your code and that code so that you can actually display the word hello world on the monitor, and then it makes it all into one file. That's called linking. And then all of this is now a binary because it's actually created the machine instructions that run down here. When you're using JavaScript and it's being interpreted, the browser is doing those steps for you. It's reading your code, kind of just like the compiler in a sense. It's creating the machine instructions on the fly, and it's sending them down to the computer. So remember, at the hardware level, we're dealing with transistors that are simply acknowledging electrical signals and reading them as either on or off. And we're representing this in a software perspective with binary digits 0 and 1. So when we create a machine instruction, and we have an example here that is a made-up add instruction, some numbers of these binary digits represent the instruction. Let's say this one here, 10001. This might represent that the machine is going to perform addition. And then these over here might be operands, or pieces of data that go along with the instruction. So this might be the machine instruction to add and the numbers that we want the machine to add. And that might be how we represent this at the lowest level as a machine instruction. If we work our way up the onion the other way, so if we go here and we say, now we're working from here and we're going to come back out, what this looks like is the next stop is assembler. Now assembler isn't, I guess it's a little unfair, assembler isn't really its own abstraction layer so much. It's a mnemonic. It's a way to directly relate a easier to look at situation for us than this string of zeros and ones. So this instruction is very, very hard for us humans to digest, no matter how good you get at low-level programming. This is a little bit easier for us to digest. We're going to add two things, A and B. A represents a number and B represents a number. So that we can digest. This is harder, right? We can do it if we see it enough times, but it's still going to be a slower process for our brains to deal with. So assembler is simply a cheat. It's a way for us to say, I can type this, and I'm going to use something called an assembler that translates it into this. But it's a one-to-one correlation between the two. Generally speaking, there's one machine instruction for every actual physical machine instruction. Now, this isn't without exception. There are some exceptions to this rule with different architectures, but it's generally applicable, especially in RISC, which is a reduced instruction set computer. Now what that means is that if I have either of these things, if I have an add instruction or I have the actual machine instruction for add, that means that the computer will perform exactly one action because of this instruction. If I want it to then store the result of this add when I'm done, that will be another machine instruction that is performed by another machine cycle that actually stores the instruction. So both assembler and machine instructions, because assembler is just a mnemonic or a way for us to look at a machine instruction differently, have a one-to-one correlation with the actual machine cycle, that I have one instruction per machine cycle. A high-level language like C, Java, or any other language really, doesn't have this same thing apply. I can write a line of code in a high-level language, and when it compiles down, it may become many lines of assembler or machine instruction. Let's take a look at that process a little bit visually. So this isn't a compiler course, and I don't mean to make it out to be. This is just a quick kind of look at what's going on to get us from your code to the actual binary. So up here we have a C function, and this C function takes in an integer array and an index, and it's basically going to swap whatever value is at that index with the next index is effectively what this thing is doing, and that's all it does, and it's going to keep that. So when we take this and compile it, it may translate into assembler that looks something like this. Here we're going to load a first value into a register, we're going to add that value to another value, and then we're going to perform some other operations, right? This keeps going. We're not going to do all of the assembler yet because we're going to save that for when we actually do assembler. The last thing here is a branch, and that has to do with the fact that this is a function call. So this is kind of a return. We're going to, again, talk about that later. Now, all of these lines of assembler translate into some string of binary digits. Again, it's a one-to-one translation. If I had this same exact line of assembler written down here, you would see the same exact string of binary digits for both of those lines of assembler. So this is just a one-to-one correlation. In fact, when you compile your C program, unless you purposely stop it at the assembler stage and say, output this compilation as assembler, it's going to actually take your C program and compile it directly to machine code as a binary. But you can stop it in between and say, wait, stop, make this output as assembler. I want to see it that way first. So what's so great about the high-level language? Why don't we just all learn assembler? Well, high-level languages have a lot of advantages. One is that it allows us to think in a more natural language. Well, C isn't, the absolute epitome of ease to read, especially nowadays. This is a lot easier to digest than this. And even if you've done assembler for a long time, most people who are familiar with the C syntax language can look at this and pretty quickly understand what's going on here. This takes a lot more time to digest, even if you've been working with assembler for a long time. They also allow languages to be designed for an intended use. So we have programming languages like R that are very good at certain things that have to do with, say, statistics and data science. We have languages all over that we can now use that are specialized to particular tasks. They also improve productivity. So it's much easier to train new programmers on a high-level language than it is on assembler. Assembler is very hard to learn. Now, that said, once you do know how to program, I believe it's very important to understand assembler. Not that you have to be a guru in it and a master of it, but understand the basics so that you can be the best programmer in whatever programming language you do choose. And lastly, it allows programs to be independent of the computer on which they were developed. And the reason why is this compiler. Now, if I take this same code in C, I can use different C compilers to create different assembler from this same function. So that means that I can compile it for, say, a Windows machine on x86. I can compile it for a Linux ARM machine. I can compile it for all sorts of embedded devices that have a C compiler. Anything that has a C compiler that will understand whatever C I've written and whatever libraries that I've called upon, I can use that compiler to create unique assembler that will work, and the instructions that go along with it, that will work for that platform. It's an effective level of abstraction that allows us to write our code once and then compile it to run on different platforms. It's a little bit different from, say, like Java. What Java does is allow you to write your code once, and then that is brought down into what's called an intermediate language. And that language runs, in Java's case, on a virtual machine. So Java has this virtual machine, and the virtual machine effectively replaces the operating system and that whole stack. It's the level of abstraction between your hardware and your software. So when you compile your Java program, you create what's called bytecode. Bytecode is something that the Java virtual machine knows how to run. All Java virtual machines know how to run bytecode. And then if you make a Java virtual machine for all the platforms you want to run your Java on, then you can just distribute that Java bytecode to all those individual platforms. So it's a little bit of a different model, but it largely accomplishes the same goal.